Hi, welcome to this particular lab class. In this lab class, we will be showing it to you how to operate a microscope and look at various sensors using the microscope. Alright. Now, you may have already seen in one of the lab class that we have basically 3 microscopes. One is a stereo microscope, second one is a inverted microscope, and third one is a metallurgical microscope, correct. Then there are advanced microscopes like scanning electron microscope, transmission electron microscopes, right. There are fluorescence microscopes and many more. What we will be showing in this lab class is how you can see the sensor under the microscope and identify whether sensors are fabricated correctly or not. For example, if I show you the interdigitated electrodes, whether the width of those interdigitated lines are 10 microns, if we have fabricated for 10 microns or not, whether the spacing between 2 electrodes is 10 micron, are the electrodes short, are the electrodes broken, right. This everything you can see with the help of the microscope. So, how to use microscope to inspect your sensors, this is the part of this particular lab, and again Anil, who taught you earlier how to deparaffinize tissue, right, he will be taking care of this particular component. We have designed the set of experiments specifically focusing on sensors and actuators, so that you get a very good idea not only from the application point of view, which I cover in most of the theory classes, and from fabrication point of view, but also from performing the simulation, which is COMSOL multiphysics, right, and then applying it with the integration of signal conditioning modules, sensors with signal conditioning modules, which large part of it another TA has taken a part of the lab component, and then showing you each lab separately, so that you understand what are the characterization tools. Further, if you have seen in one of the lab component, we have also taught you how each and every component of a vacuum system looks like, right, and that is not that just for this course, okay. We are at the right time because I got this new equipment in the lab, and before we keep it together, we have all the components for you. So, it is a very good thing, because generally we see the entire equipment, what is within the equipment, what is inside the equipment. So, this is what we have taught you in the lab class. It is a physical vapor deposition technique, is a thermal evaporation cum E-beam evaporation, or thermal evaporation / E-beam evaporator. You just focus on this, because these sensors that he will be talking about or showing you in the microscopes are fabricated using this particular equipment and other equipment, and this equipment that we will be we have shown you in the lab is called thermal evaporator, where it will help you to deposit different metals onto the substrate. Same way E-beam evaporator also helps you. I have taught about E-beam and thermal evaporator in a theory class, so you can recall that particular sections, alright. So, I will request Anil to take over and show you sensors, you show them sensors under the microscope and how they look like, right. Okay. So, I will see you in the next class, till then you take care, bye.
Welcome to this module. In the previous module, we saw a silicon wafer that was fully deposited with gold, and I told you what is the thickness, how do you design it and all, right. So, today I am going to show you one small sensor that we have made by patterning that same gold, okay. So, I am just holding it up in a tweezer in my hand. You can see it in my hand. So, it is patterned. There are lots of twists and turns on this design, but the interesting thing is that when you look it under the microscope, at every turn you can see an interdigitated electrode structure of 200 nanometer spacing and width. That is the precision. So, this device was made using electron beam lithography, not optical lithography. You have learned about optical lithography, right. Why we have gone for electron beam lithography? It is because, so you can see the device very clearly. So, you can see that there are a lot of right turns and left turns, right, but I will show you under the microscope that these left turns are not continuous, left or right turns are not continuous, and at the junction of these turns there is actually interdigitated electrode structure, okay, which is fabricated using electron beam lithography. Now, why electron beam lithography? It is because optical lithography can have only up to 2 micron or 3 micron feature size. Anything below that, because of the inherent nature of the light that is used, we use a laser, UV laser, we cannot go lesser than that, because it is fundamentally about interference patterns and what is the pattern that is formed on the wafer, correct? Now if you go for electron beam lithography, electron beam wavelength is much smaller than visible light or anything in the optical spectrum. Okay, with that you can find out by hc by lambda relation, Planck's relation. What is that? H nu, electron energy is equal to h nu, which is equal to hc by lambda. So electron beam has a higher energy. Okay, so that means that lambda will be smaller, very low, hc by lambda. So we can go to very small wavelengths, and the smaller the wavelength, smaller the feature size that you can obtain on the wafer. That is the fundamental science behind it, the physics behind it. You should understand these things very well before, because so then you will understand that whatever we make practically is inherently tied to a lot of mathematics and physics, which is very wonderful. Now so I told you that electron beam is used, hc by lambda relation. So lambda, very low lambda, very high electron energy. So we use electron beam to make these patterns. Okay, so you saw the wafer. Let's look at it under the microscope. So we are using a metallurgical microscope to view this sample, and we might have to go up to almost 20x magnification to see the features. So let me switch on the monitor. So this is a metallurgical microscope. You have seen about this microscope and all in part of this course. So I have kept the sample here under 10x magnification. Okay, here you will not be able to see what is there. We will see in the screen. Okay, now the sample is kept and the objective is focused at 10x magnification. Now we will be looking at the screen. So now I have focused it onto the screen. So you can see that the continuous lines that you had seen in the sensor, you can see a junction where there are electrodes. See, you can see this junction. So you can see the junction between these, and the electrodes are there. So you can clearly see it now. I have adjusted the auto exposure. So this was seen originally as a continuous line. But you can see that there is a discontinuity where there are electrodes, correct? Here you can see very nicely. Now let's go to a higher magnification. Just keep looking at the screen. We'll go to a higher magnification, 20x magnification. So I've gone to a higher magnification on the same device. So you can see it more clearly, that finger structure. Even now it is not very clearly visible. So let's go to 50x magnification. I am at 58 magnification and I am adjusting the focus. Now you can see the interdigitated electrode structure here. These are the main electrodes. You can see the interdigitated electrode structure at 50x magnification. Very delicately we have to move the substrate. So you can see the electrode structure. I can even go to 100x magnification and show you. I am going to 100x magnification now. This is 100x magnification. Let me focus it. So I have focused it at 100x magnification. Let me increase the exposure. So I have focused it. So you can see it now very clearly. So this is main electrodes. You can see the interdigitated electrode structure very clearly. Interdigitated, digits are there, no? Interdigitated. This we have explained a lot before. So this is very, very small. You observe, we started at 5x magnification. Now we have come down from 5x, 20x, 50x to 100x magnification to look at this. So that means how small the feature is, you can imagine. So these are all 200 nanometer thickness and 200 nanometer width and spacing interdigitated electrodes. These can only be made using E-beam lithography. This sensor was fabricated using a very special process where we have combined both optical lithography and E-beam lithography. So these major big lines, right? These big lines were made with optical lithography. These small lines were made with E-beam lithography. Why? Because optical lithography transfers the pattern fully onto the substrate in one go. E-beam lithography has to go and write that pattern. So if you try to do the whole thing using E-beam lithography on a 4-inch silicon wafer, it will take days to finish the lithography. That is why major lines we use with optical lithography, and these fine features, only those fine features we will do a direct writing using E-beam lithography. So I think you understood a very beautiful concept of different lithography techniques and actually saw a sensor here. So like this we will see a few more sensors, and later on we will even see how these sensors can be tested with biological samples. So as you have seen a unique sensor which is kept here, which was fabricated using a combination of optical lithography and e-beam lithography. We have seen up to hot magnification we have to go to see the sensor itself. We have to go to 100x magnification. So in other modules we will see other few more sensors. I think at least 2 or 3 more sensors we will see, which are again unique structures. And then also we will see how these sensors, like what is the biological preparation that is required to test with these sensors. Like I will show you about deparaffinizing of tissues, because tissues will be used with the sensors to measure their properties. That will almost complete the lab section of this course. Thank you.